Good morning, students. Today we are going to discuss about the analog to digital converter and digital to analog converter. How to interface them to the microcontroller. So, as we know that the analog to digital converter is used for converting analog information to the digital format. The digital to analog converter is used for converting the digital information to the analog format. Depending on the requirements, we are going to choose either the ADC or the DAC based on your requirement. In this class, we are not going to study about the different methods which are used in converting analog information to the digital and digital information to the analog. It is out of scope of this particular topic. As per our syllabus, we are simply going with the how to interface the analog to digital converter and digital to analog converter to the microcontroller, and also what are the factors which we are supposed to consider when we are trying to choose a particular analog to digital converter in a particular system design. Okay. So here, when you are going for interfacing the analog to digital converter, so what are the factors which we are supposed to consider? Means it purely depends on how your analog information is varying with respect to the time. Okay, how your analog information is varying with respect to the time. So based on that, if your analog information which you would like to measure and convert into the digital formats is varying very fast, then whatever the analog to digital converter which you are choosing, whose conversion time should be greater. We are supposed to choose analog to digital converter which is having the great fast conversion time, which is having the fast conversion time. And another case is how the information is varying. Means if you are taking one of the example of analog to digital converter, means the element how the input signal is varying. For example, I am taking the temperature transducer. So temperature transducer, in the sense it is going to be for every 1 degree change in the 1 degree centigrade change in the temperature in the atmosphere, then it is going to be shows the output as a 10 millivolts. It is going to show the output as a 10 millivolts. Means for every 1 degree variation in the environment, then the output is going to be 10 millivolts increment. 10 millivolts increment. So if the information is varying like that, you are supposed to choose your analog to digital converter whose quantization is going to be satisfies our requirement, like 10 millivolts. Means if at all there is a change in the input of the in the diagram, I'm just circling on the screen, so you just focus on that. If at all this input voltage is changing 10 millivolts in step size, then if we are having the equivalent output binary combination, then we can choose that kind of analog to digital converter to perform the conversion operation. Okay. So the another case is when you are taking the analog to digital conversion, as we have seen in the previous cases during the instrumentation case, analog to digital conversion means you are supposed to focus on the resolution of your analog to digital converter. So resolution of your analog to digital converter means you are supposed to focus on one formula called as a this one. So if you want to calculate the resolution, then you are supposed to focus on this formula, which I am rounding on this particular one. Yeah, over here. So it is a 1 by 2 to the power of n minus 1. 1 by 2 to the power of n minus 1. So this one is indicating the resolution, or I can say that if at all your input voltage is varying from minimum to maximum voltage, assume that the analog information is varying from the 0 to 5 volts, then that particular 0 to 5 volts is going to be divided into step sizes, equal step sizes. That is going to be decided by the resolution. That is going to be decided by the resolution. How many steps you are, means how effectively you are splitting the region from 0 to 5 volts in such a way that in every step change, means for every step change of the analog to digital converter, we are having the same step change in the transducer, which is converting the physical information into the electrical signal. So we are supposed to choose that kind of analog to digital converter. So in the textbook, what we are doing is they have taken the 102, that is a 10-bit analog to digital converter. If we are having the 10-bit analog to digital converter, then obviously the resolution is going to be 1 by 2 to the power of 10 minus 1, means the step size is going to be vary, but the resolution is going to be very small. We are able to reduce the resolution. So the step size is going to be how many steps it is going to split the entire region from the 0 to 5 volts. It is going to be 2 to the power of 10. 2 to the power of 10 in the sense it is going to be the 1024. So resolution is going to be decides how effectively the information is converting, and the step size is the one which is showing that how many splits are there from the minimum to maximum voltage range, which is varying as an analog input, And another case which we are supposed to consider is the conversion time in the sense, if your input analog voltage is varying very fastly, and whatever the analog to digital converter which you are choosing, if it is not varying that much, which is not performing the conversion operation with the same speed of the analog input change, then definitely we are going to miss some information. Then definitely we are going to lose some information because of the speedness of the analog to digital converter. So what I mean to say that if your input voltage is varying very fast, we are supposed to choose the same kind of analog to digital converter, which is having the high conversion time, so which is converting the information very fastly. So that kind of analog to digital converters we are supposed to choose. Okay, that purely depends on your scenario in which you are using. Okay, okay. So here, as I said, when you are going for the analog to digital conversion operation, as we know that the analog information is converted into the digital by sampling the analog information, which we already studied in our electronics and instrumentation case. So there we are having one factor called as a sampling frequency. Sampling frequency means how fastly the analog information is converted into the discrete format, from there to the digital format, from there to the digital format. So when you go through in that one, then you are supposed to consider the sampling theorem. Sampling theorem says that the analog information should be converted into the digital format with a rate of twice the input signal frequency, twice the highest frequency component of the input signal, So that is what we have seen in the previous classes. Okay, now. So as we know that when you are converting the analog information into the digital format, then we are having the step sizes now. So means the region, if at all I am assuming that the input voltage is varying from the 0 to 5 volts, and which is split into equal 1024 slices, means if we are having the 10-bit analog to digital converter, which is splitting the region from 0 to 5 volts in step size of steps of 1024 steps, in 1024 steps, then at that time each step size is going to be the 4.8 millivolts, 4.86 millivolts, which we have seen in the previous classes. So I'm just taking that value. So it is going to be each step size is going to be the 4.8 millivolts, means for every 4.86 millivolts input change in the analog information, then at the output of the digital analog to digital converter, we are having one binary combination. We are going to get one binary bit combination. Okay, now we are going to get one binary bit combination. But if the analog input is not changing in the steps of the 4.86 and it is changing in steps of the 4.9 millivolts, obviously there is a quantization error. Quantization error means expected value is a 4. ADC expected value is a 4.86, but the analog information is in the 4.9 steps. Then definitely we are coming across some loop that is nothing but 0.04 millivolts of the quantization is going to be occur. So you are supposed to consider all these factors when you are choosing a particular analog to digital converter, which is going to be reduces our quantization error, Again, I am saying that it purely depends on whatever the whatever the transducer which you are using in your system to measure the analog information and send that information to the analog to digital converter, and based on that changes, means how it is changing the physical entity into the electrical signal. Based on that, we are supposed to choose the proper analog to digital converter, and also how fast the input signal is varying. In the same manner, our analog to digital converter should convert our analog information into the digital format. So let us go back to the diagram. If you see the diagram over here, in this case, what we are having is we are having it is a 10-bit analog to digital converter. The IC number for this one is, as we are seeing on the screen, which is a AD571. So here it is this particular analog to digital converter is converting the analog information into the 10-bit digital format, 10-bit. digital format. And here this device, this analog to digital converter requires what is that, two power supplies. One is a minus 12 volts and another one is a 5 volts. If two power supplies means sometimes we are going with what unipolar variation as well as a bipolar variation. The signal is going to be by unipolar means the signal may have the only the positive voltages. Bipolar means the signal may be varying from negative voltage to the positive voltage, negative voltage to the positive voltage. And in this case, this particular IC is having the two ground signals. One is analog ground signal and another one is a digital ground signal. And here we are having the what is it, one signal called as a BLK, blank, and another one is called as a DR is nothing but the data ready. So whenever you would like to, if you see this one, let me show you that. If you see this one, the BLK, see this BLK is a input to this particular analog to digital converter, which is sent by the microcontroller to the ADC. So saying that whenever this one wants to start the conversion, then it is going to be sense this signal to the analog to digital converter, so that the analog to digital converter is going to be starts its conversion. And if you see the bottom one, that is a data ready signal. So this particular bottom one is a signal coming from the analog to digital converter to the microcontroller, which is indicating that whenever the conversion is done, then in order to inform to the microcontroller the conversion is over, it is using the signal called as a data ready signal. So whenever the microcontroller receives the data ready signal from the analog to digital converter, it will read the information from this particular lines coming from the analog to digital converter. Okay, and it is going to be stores the information. So in brief, when we are going for the analog to digital converter, it is converting the analog information into the digital format. And choosing a particular analog to digital converter purely depends on your analog information, how effectively it is varying and in which steps it is varying, and what is the minimum voltage and what is the maximum voltage. So based on that, we are supposed to choose the analog to digital converter. So if at all we know the what is the step sizes coming from the analog to analog variations in the analog information, if we know exact one, based on that we can choose the analog to digital converter based on its resolution as well as the step sizes, Okay, so that is what you are supposed to consider when you are supposed to choose a particular analog to digital converter. And how the analog information is converted into the digital format, that entire thing is explained over here. You just go to the textbook. If you see this one, if you see the block diagram, in the diagram, what we are having is we are using the BLK signal and the DR signal. So as I said, the BLK is to start the conversion. So BLK is to start the conversion. After starting the conversion, if you see this one, it is active low signal. So after starting the conversion, after some duration, after starting the conversion, after some duration, the data is going to be available. Because of that, the data ready signal is going to be generated by the ADC to the microcontroller. And once it is generating the ADC, after some delay, the microcontroller is going to read the information from the data lines to into the microcontroller. So that is what we are having over here. Okay, now. So the next case is we are having a digital to analog converter. So digital to analog converter means we are supposed to convert the digital information into the analog format. If at all your information is transferred by the microcontroller, it is obviously there in the digital form. But if you want to display that information on the analog screen or to the analog devices, or screen or the analog devices which are there in the further connections. So if you want to send that information, then you are supposed to use the digital DEC to convert the digital information into the analog format. So in this diagram, in the same diagram, we are having the digital to analog converter over here. Okay, now if you see this one, this is a digital to analog converter. And this digital to analog converter IC number is a 0809. So which is taking the input in the 8-bit format, and which is converting the input information into the digital information into the analog form. But here the tricky is when you are using the 0809 IC as a digital to analog converter, it is showing the digital information into the analog form in the form of the current, not in the form of the voltage. So here in this circuit diagram, whatever this circuit diagram we are having, This circuit diagram is used for converting the current information into the voltage format. Means it is a current to voltage converter. If you would like to see the information in terms of the voltage, not in terms of the analog form, not in terms of the current form, then we are supposed to use what current to voltage converter. So this particular op amp is acting as a current to voltage converter. That's it. Okay. So this is all about our digital to analog conversion and analog to digital conversion. So the next case is let us go to our what is that? Yeah, as per the syllabus, what we're having next topic is yeah, robot arm. So robot arm is just one of the application of the position measuring device. So if you see this one, I think I'm having in the what is that in vertical format. It is not in the regular format. So we are using the position measuring elements. So position measuring elements means here robot arm means we are using one transducer which is going to be we are using one transducer which is going to be measures the position of the what is that a particular element. So that transducer is called as a position transducer. So in this case we are using the position transducer to measure the position of a particular element. Application, the position transducer application in the robot arm means I would like to calculate the what is the present position of the robot arm. Means we are using the position transducer in sensing the position of the robot arm, in sensing the position of the robot arm. Okay, now so means it is one of the application of the position transducer, position transducer. So when you want to know how it is going to be calculate the position of the robot arm, position of the robot arm. Here in our case, what we are doing is we are using one transducer. Let me show you that one. Yeah, this is what we are having. So over here we are yeah, over here. So I'm assuming that it is a motor. This particular motor is nothing but which is showing the robot arm. So assume that if you are standing on the ground and your hands are in the rest position, obviously your hands are perpendicular to the or I can say that the vertical with respect to the ground. They are in the vertical position with respect to the ground. So if I'm assuming, if I'm taking that one as a reference value, that is a yeah, reference value means rest position of my robot arm. From there, as per this diagram, in this explanation, we are assuming that the robot arm is changing its position from the rest to the maximum of 120 degrees. Wait a minute, that is a 120 degrees, not 1200, it is a 120 degrees. I don't have that one, right? Wait a minute, let me show you that same thing. Okay, so it is in the 120 degrees. Okay, so the maximum angle means the maximum rising position of my robot arm, I'm assuming it is a 120 degrees. I'm assuming it is a 120 degrees. Okay, so yeah, right. So here as I said, in order to move our robot arm, see everything is good in a robot. Each and every part we are having the transducers to measure the some parameters like what is the position of the your leg, what is the position of the means you not your leg, it is a robot leg, and what is the present position of the robot, what is that head, all those things means we are having the transducers allowing in the inside the robot to perform certain activities, obviously. Okay, now so just like that, here also we are using the one position sensor as a what is that robot arm position measurement. Means we are using the position transducer to sense the present position of the robot arm and to change the present position of the robot arm also. Means depending on present position, after measuring the present position of the robot arm, we can send some signals to the signals from the heart of the robot arm to the corresponding transducer to change its position from the current position. Okay, so that is what we are having. So here what we are doing is we are using one part as a transducer. We are using one part as a transducer, which is following the 2:1 gear ratio. 2:1 gear ratio means whenever there is a again I'm having a mistake. Wait a minute. Wait. Wait a minute. So this one should not be there. I took it as well for this one. For this one. Okay. Yeah. So here it is a 2:1 gear ratio. 2:1 gear ratio means whenever there is a 1 degree variation in the robot arm position. So obviously we are calculating with respect to the angle, right? From the reference position to the certain height. Everything is going to be calculated based on the angle. Okay. So here whenever there is a 1 degree variation, then the part is going to be convert that information into the 2 degrees. Means 2:1 gear ratio means input is a 1 degree, then the output which is going to be shown by the pot is a potentiometer is a 2 degrees. Okay, so right over here we are taking the what is it interfacing of means this particular robot arm structure is connected to the partner. So here we are having the potentiometer. So this particular potentiometer is a single turn potentiometer whose resistance is going to be the 1 kilo. So whose resistance is going to be the 1 kilo. It is a 1K part. It is a single turn one, not the multi-turn. It is a single turn one. And assuming that in the structure, I'm assuming that turn means we are going to consider each turn of the pot as a loop, and each loop is going to be shows 2.85 what is that ohms. Each turn resistance is going to be the 2.85 some ohms. So that we are going to see in the textbook. I'll go back to that one. So just remember that here we are having this entire structure is to this is a position of the robot arm right now, and we are able to this is a position to hold the robot arm, and this one is going to be varying from minimum to maximum, which is a 0 degrees to the 120 degrees, and here we are having the part. So this entire setup converts the motor. So obviously wherever we are using the hands or any elements inside the robo, we are having the so many motors. Based on the motors only the robots are working, right? So here this particular motor is showing the is one which is going to be changing its rotation to raise the robot arm to raise the robot arm. Where is my to raise the robot arm to down the robot arm. So that is going to be controlled by the motor. So this is a robot arm motor to rise this element as well as to fall this particular element. Okay, so that's what the intention of this particular motor. So here whenever there is a 1 degree variation in the robot arm, then obviously the potentiometer is changing its value in terms of the 2 degrees. So let me go back to my textbook. So we have the textbook, right? So here what I'm doing is I'm taking the pot as a pot as a transducer to measure the present position. So whenever the pot changes, means whenever this value is changing, whenever this one is changing, obviously the voltage drop is going to be changes. So here what we are doing is they are taking some mathematical calculation. Don't worry about it over here. So we took the 1K partner. So this is 1K partner. So this 1K part, I'm assuming that this 1K part, entire 1K part from here to here, it is giving the what is it, 350 degrees. It is giving the 350 degrees of turns. So each turn is representing 1 degree, 1 degree, 1 degree. But what I'm going to do is here, if at all in this example, as per this diagram, the number of turns are the 350. But if you are going back to this one, in the example, he is assuming that the number of turns there in what is that pot, the number of turns are there in the pot is a 270 turns, and each turn is going to be have the 2.857 ohms per loop. It is going to be the 2.857 ohms. So here the main intention of this formula is to calculate the resolution. So as we know that when you are converting the analog information with the digital format, we are supposed to focus on the resolution. For that only he is taking this calculation. If you are getting confused with this one, then you can skip off this explanation that calculating the resolution, all those things. You can simply say that the motor in this particular topic, we are simply measuring the present position of the robot arm, and we are converting that information into the analog format. Analog information is converted into the digital format using the analog to digital converter. In our case, we are using the PIC 16671 microcontroller, so that's why we are having the integrated analog to digital converter, which is going to be perform the conversion operation. We'll least bother about that one. So here we are expecting that whatever the part we are taken, this one is a 1:2 ratio. 1:2 ratio in the sense whenever there is a 1 degree variation in the robot arm position, whenever there is a 1 degree variation in the robot arm position, obviously the output of the part is going to be shows its variation as a 2 degrees. So the minimum robot arm minimum position is nothing but the reference position is taken as a 0 degrees, and the maximum rising capacity of the motor, that is a robot arm, is a 120. Then obviously the output of the part is going to be varying from 0 to 240 degrees. 0 to 240 degrees. So in this conversion, he is in this structure, he is what he is doing is exciting this particular part. This particular part is connected to the 6.86 excitation voltage, to the 6.86 excitation voltage. Okay, now so this particular 6.86 excitation voltage, as we are taking this much of voltage as a excitation voltage for our part, so he is expecting that whenever we are having the 250 degrees from here to here, whenever we are having the 250 degrees full scale, then the output of the part is going to be it is going to be in terms of the voltage format. Now position is in the physical format, it is converting the position, which is a physical format, into the electrical signal by using the part. So this part is changing, or I can say that it is a part with the third terminal is connected to the this particular robot arm. Okay, now so whenever there is a change, then this terminal is moving upward or in the downward direction to indicate its present position. Okay, now so here he is saying that whenever we are having a 255 degrees split, 255 degrees what is that, the angle which is measured on this particular pot, then the voltage, full scale voltage, is going to be the 5 volts. Full scale voltage is going to be the 5 volts if the excitation is in the 6.86 voltage. That purely depends on excitation voltage. So here, based on the excitation only, we are means based on this particular excitation only, he has taken these numerical values. Nothing to worry about that one. Just remember that whenever there is a change in the robot arm position, 1 degree change, that is going to be converted into the 2 degrees format. That is going to be converted into the 2 degrees format. But here in our case, the maximum voltage is going to be the 4.731 as per this calculation, as per the excitation voltage calculation. The maximum voltage which we are going to get is a 4.731, because it is going to be what maximum is, how much maximum is a 120 degrees only. Maximum robot arm position is a 120, so that is converted into the electrical signal format, which is a 4.731. Full scale is going to be the 4.731. But whatever the analog to digital converters which we are having inside the PIC 16C71 family, that is going to be the 8-bit converter. That is going to be the 8-bit converter. Means it is converting the what is that? It is converting analog information into the equivalent to 8-bit format. But what is the minimum voltage, minimum angle? Over here in our requirement, it is going to be the 0 degrees. Maximum is a 120. But here, when we are having the 8-bit analog to digital converter, so obviously we are going to get the 256 combinations. 256 combinations. So, but we require only the 120 combination, not the 256. So that's why what he is doing is he is taking the 8-bit to represent the what position of the to represent what the position of our robot arm in terms of the 0.5 degrees change. In terms of the 0.5 degrees change, means whenever there is a 0.5 degree change in the robot arm position, obviously it is going to be shown by the pot as a 1 degree, by the pot as a 1 degree. So as we are taking the decimal value, then entire 8 bits combination is divided into one 7-bit, one part is a 7-bit, another one is a 8-bit. Means we are taking the 8-bit combination. You are supposed to move from the LSB to the MSB. When you are moving from the LSB to the MSB, the first LSB bit position is taken as taken to represent the fractional value. That is the 0.5 degrees, 0.5 degrees, 0.5 degrees. So whenever you are getting the 256 combinations using the 8-bit, so wherever you are having the odd number of ones in the LSB, then obviously the position of the robot arm is going to be the 0.5 degrees, 0.5 degrees, 0.5 degrees. Okay. So based on that only, he's what he is doing is converting this. Wait a minute, I'll show on the slide so that it is going to be appear very well. So over here, so as we are having the 8-bit analog to digital converter, so we are going to get the 256 combinations, but out of 256 we are interested only in the 120. We are interested only in the 120. So 120 is converted into the 240 degrees by the position sensor, which is nothing but the pot, which is nothing but the pot. So here what is doing is, you would like to show the robot arm position for every 0.5 degrees, means for every 0.5 degrees variation from the robot arm, for every 0.5 degrees variation in the robot arm, we are going to get the equivalent binary combination. If at all there is a 0.5 degrees variation, then 1 is going to be increases, means the first LSB is going to be increases. So yeah, have you seen that one? Let me go back to this over here. So whenever there is a 1 LSB is get incremented, means whenever there is a 1 LSB, otherwise you know the odd number and the even number, right? If the odd number is if we are having the odd number, then obviously the LSB is going to be 1. If we are having the even number, obviously we are going to get the even LSB position as a 0. Okay now. So here we are having the LSB whenever where there is a 0.5 degree variation, whenever there is a 0.5 degree angle variation from the robot arm, then obviously the LSB is going to be 1. Whenever if the robot arm is going to be the 1, not the 0.5, then the LSB is going to be 0. Okay, so like this the information is converted into the analog format, into the digital format. So in brief, the application of this particular robot arm is a example for position transducer. With the help of the position transducer, we are calculating the present position of the robot arm. So in this case, the pot is taken as a. Pot is taken as a position measuring transducer. If you want, you can use the LVDT also. To measure the position transducer, which is there in the next topic here, we'll see in the next class. So right now what we are having is, we are having the pot. We are using the pot as a transducer to convert our the position into the electrical signal format. So in brief, yeah, the robot arm position, when you are going to going for the robot arm position topic, it is only for calculating the present position of the robot arm with the help of the position transducer. Here we are taking the pot as a position transducer. So if you are getting confused this value, these particular numerical values, then you can leave this particular part, no problem. This particular combination, it is only showing the resolution. How the each turn of the pot is showing the effectiveness of the position. It is only showing the resolution. Okay, if you are getting confused this particular numerical value, you can skip off this. But whatever the voltage ranges which we are seeing right over here, that purely depends on your excitation voltage which you are having right over here. So as we know that the analog to digital converter, which is residing inside the PIC 16671, is a 8-bit analog to digital converter. So but our requirement is for the 7-bit only. If you are taking the 7-bit, we are going to get the 128 combinations. Okay, that is more than enough. So but as in order to make use of the 8-bit analog to digital converter as a 7-bit one, they have taken the LSB to represent the 0.5 degrees position. Whenever there is a 0.5 degrees variation, and then for every 0.5 degrees variation at the output of the analog to digital converter, we are going to get 1 bit combination. Okay, so this is all about your robot arm position in microcontroller syllabus. So in the next class, we are going to know about the LVDT. LVDT is also one of the example for position transducer. So as you know that the LVDT is nothing but linear variable differential transducer. So that main intention of the LVDT is to indicate the position of the element which is connected to the core of the LVDT, whether it is at the reference position or whether it is moved to the left side of from the reference position or to the right side to the reference position. So that is going to be calculated based on the LVDT. So LVDT is one of the position sensing transducer only. So you can take the LVDT as a position sensing transducer. Okay, so we'll continue. We'll go for the LVDT and RPM meter, digital thermometer, and other things in the next coming classes. Okay, so this is about what is that? In this class, we covered the analog to digital converter, digital to analog converter, and the robot arm. Remember that we are not going for different methods available in the analog to digital and digital to analog converter. We took one example, one analog to digital converter. We test that one to the 8051. That's a microcontroller, any microcontroller which is not having the integrated analog to digital converter and digital to analog converter. Okay, so this is all about this class. So if you are having any doubts, you can raise your doubts in the group. Okay, thank you. That's all for now.